took a shortcut here, but remember, you can't have a hydrogen ion by itself in water. The 10 to the minus 8th molar one was a common ion problem where we had to take into account both the water, hydrogen ion from the HCl and the hydrogen ion from the water. Over here, when I was talking about the weak acid, and we calculated that the hydroxide ion was 10 to the minus 12th, I said the hydrogen ion from the water was also 10 to the minus 12th, but we could ignore it. If I brought that molarity down to 0.0000 something or other, then we couldn't ignore it, but I said that's not a problem we're going to do. But the problem we have to worry about here is something like this. I'll use calcium fluoride, not calcium fluoride. Here, this right now. Point 1 minus 10. What did it go off? The first thing somebody always says, you didn't tell us what that meant. That's because I expect you to know that. If you don't know your solubility rules, this tells you this must be soluble. You can't prepare a 0.01 molar solution unless you can dissolve 0.01 moles. So if I gave you a bunch of compounds you never heard of, and we didn't study the solubility rules, and I say the molarity is 0.25 molar, what does that tell you? 0.25 moles of that material must have dissolved in enough water to make a liter. Otherwise, you can't make a 0.25 molar solution. So the KSP is not applying to this. What does it leave? It leaves this thing. Okay. So that's the one it must apply to. And here's the solution you would start doing. With something like and by the way, with acid base, you can get by without writing the equilibrium expression because they all look the same. But when you start doing KSPs, you should always write the balanced equation and always put in the mole ratios to remind you how that goes, because each one of these is going to be different. This says the concentration of silver ion squared, concentration of chromate ion, because that's what the equilibrium expression says. It's KSP, you don't bother with that. So here's the silver ion, 2x squared, times the chromate, I just wrote it in that fashion, 4x cubed, and this is the answer I would see. concentration of chromate. And 6.50 times 10 minus 5. And everybody's happy till they get the quiz back and they get next to 0 points. And the reason for that is, this is now the common ion problem. And one of the things I always say, stoichiometry first, equilibrium second. You'll hear me saying that a lot from now on. What happens is, potassium chromate is soluble. Notice this is an equilibrium, but this is a really, really small number because it almost all goes into ions, 99.999, whatever. So what you get, this is equal to, looking over there, and this is 0.0. Okay. Then you're ready to start the equilibrium problem. And your I column is different because you already have chromate in there. This is still 0, this we don't care about because it's not an equilibrium expression. So what you're going to have is, we'll still call this minus x, this is plus 2x plus x. And now the problem we have to solve said, that's a cubic equation. You said we'd never have to solve cubic equations. Unless, what? We do an approximation. You say x must be small because this number here is 1.1 times 10 to the minus 12. So x is probably pretty small. So I'm going to say it's approximately equal to 4x squared. I don't want to put it outside the parentheses because I already squared the number. 0.1. Okay. Yes?
Wait, where'd the 0.1 come from? So is it 0.1 or 0.01?
What did I say? Oh, okay. What did I say? Where's my problem? It's 0.01.
Oh, okay.
Good, got that before I made a mistake all the way at the end. So it's 0.01, but this is still 10 to the minus 12 with 0.01. The x has to be much smaller than 0.01. If it's not, I might have to do more approximations. Okay? But now I can do the arithmetic. It's really easy. I just divide and take a square root, multiply and divide and take a square root. So,
Also,
mm-hmm.
let's make sure. Is the stuff we did on the left? That's just wrong? We shouldn't do that at all, or what's?
What? S?
No, on the left, like the first part we did with the AgRCO4 with no chromate oxide.
What I said is, this is what people do, and then this is what I do.
So that whole thing's wrong.
That's wrong.
Okay.
Right.
I need to not. Okay.
That is wrong because you forgot to take into account the extra chromate ion. That's why it's wrong. Okay. This is the new type of problem. And I said the reason we saved this for last is because people always mess this one up because they forget to put that in there. We are used to just taking square roots and cube roots or whatever, and you have to worry about the common ion. And we'll see why we cause, and also I did this because I wanted these numbers for comparison purposes. So basically what I started out to do was I'm going to say x, which is equal to what? Nothing, it's molar solubility. Okay? So x, here's where I start to do this now. Is 5.24 times 10 to the minus 6. So that says that the silver ion times 10 to the minus 5. Okay. What's the chromate ion? Says it's the three significant figures, it hasn't changed. Now this is what is called the common ion effect. If you look at silver, its concentration went down by a factor of 10. Went from 10 to the minus 4 to 10 to the minus 5. It's the common ion effect. In other words, it's reduced the concentration of silver ion that remains behind in solution. Where do we do this all the time? In the lab. Whenever you check for completeness of precipitation, you're always adding an extra drop of the precipitating reagent. That means it increases. One of if you're trying to precipitate silver by using chromate, for instance, and you added the extra drop, you now reduce the amount of silver that's remaining in solution by even more. Okay? That's the common ion effect. He talks about a diverse ion effect. We're not going to do anything, but if you have other ions in there, it affects the solubility. Sometimes it'll increase the solubility, other times it'll decrease it. That's why we don't do any calculations. So he mentions diverse ions. Potassium would be a diverse ion. It might affect the solubility somehow. The potassium ion, of course, would be what? The same number we see up here because it's not in the equilibrium